Welcome back to the sixth video about the Melexis MLX90363 Triaxis registered trademark magnetometer and its increasingly annoying datasheet. Last time we had a first look at all the configuration parameters of that thing, which reside in its EEPROM, and we read out the relevant 16-bit words from the EEPROM using a new MOSI and MISO message, the memory read message. Card here, link in the description. Unfortunately, due to some, let's call them inconsistencies in the datasheet, we missed two of those parameters. So this video will start out with a little errata, where we have a look again at the real memory map of the EEPROM that I modeled as a Enum. And then we will go ahead and actually convert all these parameters in some really readable values and not just staring at 16-bit hexadecimal values. Enjoy! And here's now the hopefully complete enum class address listing all the documented addresses within the EEPROM. I changed a little bit the command structure here. I have now fixed columns, a parameter that is the parameter that is within the certain bits of an address. The chapters within the datasheet where that parameter is mentioned and explained, and then that was just a copy and paste the original command out of the datasheet for that parameter. We won't go over all of them, just over my mistakes. So the first mistake in the previous version was that I had here assumed address 1030 between 1028 and 1028. Totally my fault. I somehow switched from counting hexadecimal to decimal, and the next decimal, even decimal value after 28 is 30. Then I mentioned two parameters that were not mentioned in the overview over the parameters in the datasheet, and this was at address 102C, the odd cell. We will hopefully find out what that is doing, and it's not mentioned in that overview chapter 15. It's missing there, but it's mentioned in a chapter 16.3, and probably in conjunction to that the parameter auth, which resides in the previously undocumented address 38. So the previously undocumented address range was from 34 to 38. Now it's only here 34 and 36, which are undocumented, I think. And that was, of course, also not mentioned in the overview chapter 15, but only in chapter 16.3. And we still don't know what that thing does. With that out of the way, let's think about how we want to model the different parameters in software, starting with the ones that kind of demand a enum. The first being XYZ, a 3-bit parameter determining the device orientation, and it does basically map the outputs of the orthogonically oriented sensors B1, B2, B3 to our axes X, Y, and Z. We have 6 values ranging in the binary range from 000 to 101. And here's the related enum class map XYZ. So we start here with the value XYZ, which simply maps B1 to X, B2 to Y, and B3 to Z. So 000, and we end with the value ZYX, binary 101, which maps B1 to Z, B2 to Y, and B3 to X. Please note that first value 000 should be the default value. I found that somewhere hidden in the datasheet. Then we have the parameter filter, which controls an FIR filter somewhere in the signal processing. And it's a 2-bit parameter with 4 values controlling how strong the filter is, ranging from 0, 0, no filter, to 1, 1, a medium filter. So you cannot really influence the filter parameters of the FIR filter directly, but you have 4 preset options for that. And here's our Enum class filter for the parameter filter. So from no filter, that is 0, 0, to medium 1, 1. 0, 0 again being the default value. That's somewhere, I think in the overview they give you the total value, default value of a word, so you can determine that. Please note that the bits here are not at the end, but somewhere within the byte, within the configuration word in the EEPROM. So a bit position here is really important. Finally, we have the pin filter parameter that does some EMC filtering on the SCI pins. It's also a 2-bit parameter, and we have here 3 options: 2 MHz 0, 1, 1 MHz 1, 0, and 500 kHz 1, 1. And here's the associated Enum class pin filter, just 3 values from SPI 2 MHz to SPI 500 kHz, binary 0, 1 to 1, 1, 0, 1 again being the default, supposedly. There's the 4th parameter that I would like to model as a Enum, ZEL as MISM. ZEL is select, and as MISM stands for sensitivity mismatch. It only has 2 values, 0 or 1, but it doesn't have the semantics of a Boolean, because if it's 0, that means that somewhere the absolute of a magnetic field strength B1 is greater than the absolute of a magnetic field strength B2, while in the case the value is 1, the magnetic field strength B1 is smaller than the magnetic field strength B2. And I modeled that in the Enum class ZEL as MISM, unsigned integer 8, just 1 bit significant here, 0 or 1. If the bit is 0, then B1 is greater B2. If the bit is 1, then B1 is smaller B2. There is one more, let's call it a parameter, that I would like to pack into a special type. And these are the free bytes. You remember, they are all over the place within the EEPROM, and I would like to consolidate them as a 5-byte array inside a struct, so I can pass them back from functions. I know they are here in the chapter given as a numeric value between 0 and 2 to the power of 39 minus 1. Oh, that's wrong. 5 times 8 is 40. So the numeric range, if you look at it as a numeric value, is actually 0 to 2 to the power of 40 minus 1. And yeah, that value here is also wrong. User ID is a total of 32 bits, so the possible values of user ID is between 0 and 2 to the power of 32 minus 1. Yeah, that's a datasheet for you. And here's that struct free that only contains that array of 5 bytes. The rest of the parameters are either numeric or Boolean. Let's start with the traceability information, which is not really a parameter, but it also resides in the EEPROM. It's 48 bits long, consists of 3 consecutive 16-bit words in the EEPROM, that is 6 consecutive bytes, and I will pack that in a 64-bit unsigned integer. Odd, which was somehow missing from the list of the end-user programmable items, is just an 8-bit integer. That's all we know about it. And odd select is a single bit that we can handle as a Boolean. Sensitivity mismatch, SMISM, is a 15-bit integer encoding a float in the range between 0 and 2. Odd B1, B2 is a 8-bit integer, also encoding a float between 0 and 2. K alpha, K beta, and KT are 16-bit integers encoding float values in the range between 0 and 2. 3 remarks here. First, this time they got the 2 to the power of x minus 1 notation correct for the integer, so the value range is actually between 0 and 2 to the power of 16 minus 1 for a 16-bit integer. Second, they completely changed the format of the table in that next chapter here. Reasons unknown, and they don't provide you, like in the last chapter, with the actual address in the EEPROM where the parameter resides. Yeah, I don't know. Virtual gain min and max don't deserve any table at all. We just have to assume from the overview that they are both 8-bit integers. Hysteresis filter, also an 8-bit integer, again another notation used here, and it also encodes a float value. 1 LSB of that integer is worth 0.044 degrees. And finally, we have the user ID. Remember, the user ID consists of 2 consecutive 16-bit words in the EEPROM. So it's 32-bit integers. Yeah, I moaned about that fault here. So it should be 0 to 2 to the power of 32 minus 1, not 2 to the power of 31 minus 1. And we'll simply put that into a 32-bit unsigned integer. So how do we implement the whole shebang? I think this time I will be jumping quite a lot between the library definition in the .h file and the implementation of the methods in the CPP file. You will see that makes more sense. First of all, we need a method, I called it config read, that reads the actual configuration from the EEPROM somewhere into a data structure. And of course, that method can fail. In the private part of the class, I have that data structure. It's a typedef union config, of course. And it's a union because we will use the same techniques that we already used in the unions for the MISO and the MOSI messages. And the first member of that union is an array words with a size 18. Remember, we have 18 documented addresses in the EEPROM of 16-bit unsigned integers. And that array should contain all the 16-bit EEPROM words that we know of. So a total of 36 bytes. Please note that the words from the EEPROM are not necessarily sequential in that array. Finally, we have a private variable actConfig, so the active or actual configuration that resides in the EEPROM of the type config. And please ignore the setConfig for now. I was thinking ahead. Here's the implementation of that config read method in the CPP file. First, I have here a constant array addresses with the 18 known addresses. And please note, I reordered the addresses a little bit. They are no longer in consecutive order. So first, I have the 15 addresses of parameters that we can actually write in the EEPROM. And that is followed by the MLX ID addresses, which we should never write. My first actual statement in the method is a send memory read for the address 0 and the address 1. And if that send memory read fails, I return, of course, false. Remember, SPI, I have to send a memory read command, and then only in the next SPI transaction I get actually back the content of the addresses I requested. So next I go into a for loop starting with the address 2, going up to less than 18 and incrementing always by 2 addresses. Yeah, with send memory read we always request the content of 2 addresses from the EEPROM. I do that delay microseconds of 139 microseconds that we need after a memory read. We already talked about that. And then I do another memory read, this time with my loop variable address and address +1. And also return false if that fails. Then I check if my last received meso message was actually a memory read reply. If that's not the case, I have a library error, opcode, and return false. Otherwise, I received the previously requested memory content. And I can write the data now into the act config words array. And I'm writing here to the address -2 and the address -1. The last memory data 0, respectively the last memory data 1. Remember, we have here the data we requested in the previous iteration of the loop, or in that case, if that's the first iteration through the loop, with our initial send memory statement here. So we requested here address 0 and address 1. Our loop variable is at 2, so address -2 is 0 and address -1 is 1. Assigning last memory data 0 and last memory data 1. Finally, we have to handle the data that we requested in the last iteration of the loop. So the last 2 addresses. So first of all, I do again a delay microsecond 139, and then I send a knob just to receive the data. And of course, if that fails, I return false. Otherwise, I again check if the last received was really a memory read. Otherwise, I throw that opcode error again and also return false. And at the very end, I write to that words array 18 -2 and 18 -1. Again, the last memory read data 0, respectively the last memory data 1. And then I return true. Now that our data is in that words array, we can talk about that struct values. And I already told you we are using exactly the same technique we used for the meso and the mosi messages. So we are treating these 16-bit words just as a flat memory of 36 bytes, and we align in our struct the variables so it makes sense for us. So first of all, we have that pin filter address, and the first byte at that pin filter address is undocumented, and the pin filter is actually contained in the second byte, but only in the first 2 least significant bits. The other bits are also undocumented. Then we have in the first word of the array, so the next 2 bytes, 2 bytes free 0 and free 1 of free memory. The next word at address k alpha, that's simple, is simply a 16-bit value. Same is true for k beta. Then we have at the address odd b1, b2, free b, have first the 8-bit value for odd B1, B2, and then another byte of that lacky free memory. The next address, 3CF contained 8 bits first byte with a next 3 byte, and then an 8-byte value for F hysteresis, sorry. Then at the map XYZ 3D and filter, we have in the first byte everything that's interesting to us, so that map XYZ, the 3D and the filter in the different bits. 2 bits at the end undocumented, and then we have another undocumented byte at that address. Auth select is orthogonal. Select is the same. First we have here an undocumented byte, and then in the next byte we have actually that bit that we translate in a Boolean for auth select, and the rest of the bits in that word are undocumented again. That is a typo here. Sorry, I will correct it in a second. Same is true for virtual gain min and virtual gain max. 2 bytes contained in one word. That was easy. Then we have another whole 16-bit word containing the KT parameter. Then at the address sensitivity mismatch, select sensitivity mismatch. That's unfortunately one 16-bit word I cannot fiddle apart any further. So the first 15 bits is that float value, selectivity mismatch, and the last 15th bit or 16th bit is the select sensitivity mismatch. Then at the address odd, we have actually a 8-bit value for odd, and the next byte is undocumented. Then user ID, a little trick. These are 2 consecutive 16-bit words, so I'm simply using here a 30-bit unsigned integer, and this gives me directly the value for user ID. Next address, free, is 8-bit 3 byte, and then another undocumented byte. And finally, we have the 3 16-bit words for the MLX ID. And that makes up our values in that big 18-bit words array. I still need a few bit masks, but only a total of 7 for the few values that do not align to full bytes or only occupy a part of a byte. And now we can implement all the rest of the config functions. And I won't go over all the functions, talk too long already about code. I will just give you a few examples. So first here we have the config pin filter, which returns a enum pin filter, and I can simply take now the actual config values pin filter and binary end that with the bit mask for pin filter and cast that to the enum pin filter, and I'm done. Config MLXID should return us a 64-bit value, but in values MLXID, that's an array of 3 16-bit words. And I'm doing that in a backwards loop. So I'm counting down here 2, 1, 0. And I initialize my MLXID to 0. So in the loop, that first shift left 16 bits does absolutely nothing. My word is still empty. And then I binary OR the highest ranking words in my MLXID array, so MLXID2, to my 64-bit value. In the next iteration, I shift that highest ranking word 16-bit to the left, and then I binary OR again the middle word, the word 1, to my value. I go again, last time through the loop, I shift the whole shebang, so the highest ranking word and the middle word, all 16 bits to the left, and then I binary OR my MLXID word 0 to the value. So I have my array with the three 16-bit values in the 48 least significant bits of my unsigned integer 64. And of course, at the end, I return the whole shebang. The method config_free will return a struct free, and remember that struct free just contains an array of 5 bytes. I have a local variable free of the type struct free, and I just fill that up 1 byte after the other with all the free variables in my values of the act config. And at the end, I return the struct. Config k alpha raw just returns the 16-bit value act config values k alpha, while config k alpha takes also that value but converts it into a float in the range 0 to 2. And 65,535 is, of course, 2 to the power of 16 minus 1. And that's the only raw and float function I will talk about, because the others work exactly the same. Config_hist is a little bit different than all the other methods returning a float, because there in the datasheet we got the information that one least significant bit of our value is worth 0.044 degrees. So I convert my raw figure into a float and multiply that by 0.044. I won't talk about any more of the methods returning an enum. We saw already that bit mask stuff. Then config3d is a method returning a bool. The technique is quite similar here. I take act config values, maps xyz, 3d filter, yeah, that contained a lot of stuff, binary AND that with the bit mask for the 3d bit, and if that's true, then I return true, otherwise false. Okay, that was all the Boolean functions. The whole config selectivity mismatch stuff is a wee bit different, because here for the raw value I have to take the 16-bit word within my values and binary AND that with the bit mask for selectivity mismatch, which is the 15 least significant bits before returning that. And I do exactly the same for the float version before I convert that into a range between 0 and 2. 32767 being, of course, 2 to the power of 15 bits, minus 1. And config select sensitivity mismatch, that was a enum. That is not a simple cast here, but I also do here a little Boolean expression with the bit mask for selectivity, select selectivity mismatch, and binary AND that with the word in my values, and if that's true, I return the enum b1 smaller b2, otherwise I return the enum b1 greater b2. And that's it. Everything else is just copy and paste and uses exactly the same techniques. That leaves us with the sketch itself. In the setup, I added here a config read, and if that fails, then I call the handle library error function. And in the loop, we just have now a serial print MLX90363 config and then a delay of 1 second. That's it for the loop. The zero print MLX90363 config method does nothing else than using all these new methods to print out the configuration of our little chip in a nicely formatted manner. And I won't go over all the code here because, yeah, it's serial print. Some case statements wherever we are handling an enum or a Boolean, and serial print, switch statement, serial print, and oh, yeah, of course, a loop over the 5 free bytes we have. Please note, I also printed out in the heading for each parameter the default value, at least as far there is a documented default value in the datasheet. And here's a rather anticlimactic result on the serial monitor. So our MLX ID seems to be 3 times 16 bits, so 48 bit. I printed that out as hexadecimal, so that seems to be correct. Map XYZ should default to XYZ, that's a 0 value, but yeah, it's correct. 3D should default to false, that it does. Orthogonal select should default to false, which it does, and the orthogonal preset, so that's a preset value by MLX individually for each chip, is 3. Odd B1, B2 should also default to 0, and the raw value as well as the float value does. Select sensitivity mismatch is preset by MLX during production, and it's B1 greater B2, so 0 value. If we're reading 0, I'm always a little bit fuzzy if that is a correct value or not. Sensitivity mismatch is also preset to a raw value of 32571, which translates to a float of 1.9880367. K alpha should default to 0, and it does in the raw value and in the float value. K beta should default to 5252428, which translates to a float of 1.6, and it does that exactly, so I'm sure we're doing that right. KT should default to 32767 or 32768. Yeah, because 1.0 is just between two of the raw integer values, and yeah, the float value is in fact 1.000000152, so close enough to 1 for me. Filter should default to no filter, which it does. Virtual gain min and virtual gain max should default to 0, respectively 41, which they do. F hysteresis is also a preset value for some reason. I don't know, because anything but 0 doesn't make any sense here. Pin filter should default to 2 MHz, which is a binary value of 0, 1, and it does. User ID should default to hexadecimal 00030001, and it does. I'm printing it out here as hexadecimal. And the free bytes should all be 0, and they are. And then we start again in the loop with the MLX ID. So I'm not 100%, but at least all the default values, according to the datasheet, are read out as those default values from the EEPROM. So, yeah, seems to work. That's it for today. Admittedly, that was maybe a little bit much code, but we implemented quite a lot of methods in our class. Anyway, now that we decoded all the parameters, I can't even find the sheet here with the parameters on the desk, we want to maybe change the parameters that is right to the EEPROM of that thing. And that's exactly what we will do next time, and it will also require some code, and it's not quite straightforward. Anyway, till then, bye!